Welcome to today's lesson. In this first tutorial, we will approximate the area under a curve using a finite number of rectangles. We are in our final part of our final topic in pre-calculus, part C, the area problem. So I have 4 copies of a curve, and what our ultimate goal in this topic is to find the area underneath this curve that is in between these 2 vertical lines and above the x-axis. In this first tutorial, we're going to be sectioning off this area into a certain number of rectangles. For example, in this first diagram, let's make the number of rectangles 1. So n is just going to be 1. I'm going to make my rectangle start in the top right corner, so my point is on the curve, and I'm going to draw a rectangle. And that's it. That's just one rectangle. Now clearly the area of this one rectangle is not the same as the area underneath the curve, but it's, well, I guess it's a little bit close. Let's see what happens if we make 2 rectangles. Let's take this area, I'm going to divide it in half and make 2 rectangles. I'm going to say here's one of them and here's the second one. So that's a little bit closer. If we found the area of each of these 2 rectangles and added it together, it would be a little bit closer to the area underneath the curve. Obviously a little bit more because there's extra area in the rectangle than there is underneath the curve. Let's try n equals 4. Let's make the number of rectangles 4. So I'm going to divide this section in half and divide each half in half. I'm just eyeballing it here. Each of these rectangles, I want the top right endpoint to be on the curve. So there's that one, and there's this one, and there's this one, and then there's this one. So that's even closer. If I added the areas of these 4 rectangles, I would get closer to the area under the curve. 3 of these rectangles are an overestimation, but one of them starts to be an underestimation. Let's see what happens if there are 8 rectangles. So I'm going to divide in half, and then I'm going to divide into quarters, and then I'm going to divide into eighths. There we go. And then each of these 8 rectangles is going to have a right endpoint. That's what this is called right there, because we're going to be doing right endpoints today. And I'm drawing each of these 8 rectangles. Okay, even closer. Yes, we still have a little extra here, and then it starts to be a little bit underneath the curve here. And if I added all these areas together, we'd be getting pretty close to the area under this curve. Obviously 8 rectangles is not enough, but what if we did 10,000 rectangles? In fact, what we're ultimately going to be doing is making infinite rectangles, adding up all of their areas, and we will have exactly the area under the curve. But before we do that, we're going to practice with a finite number of rectangles and see how close we can get. So let's look at example 1. We have f of x equals 6 minus x squared. What we're going to do is we're going to find the area between these 2 vertical lines, x equals 0 and x equals 2. And we're going to do that by adding the 5 rectangles, and we're again using right endpoints. So I actually have the picture already for you. Here's a quick sketch of 6 minus x squared. And here's tick mark 1 and tick mark 2, and I've divided it into the 5 rectangles that I want. You can see that I'm using right endpoints because the top right of each of the rectangles is on the curve, is a point on our graph. So to find the area of a rectangle, of course, we're talking area equals width times height, or length times width, or base times height. I'm going to use width and height. So I need to talk about the width of each of these rectangles and the height of each of these rectangles. Let's first talk about the width. We have an equal width for each of these rectangles. And since all 5 of them add up to 2 tick marks and we're dividing by 5, it makes sense that each of the widths would be 2/5. Here's 2/5, and then 4/5, 6/5, 8/5, and then 10/5, which of course is equal to 2. So our width is the same for each of the rectangles. The height is different for each of the rectangles. In fact, the height depends on which point on the curve you're talking about. So the height depends on the curve. So it's a function of what x is. So we've got our width is 2/5 and the height will depend on the curve. So I'm going to say our ultimate area is big A, and I'm going to say that a sub 1 and a sub 2 and a sub 3 and a sub 4 and a sub 5 are our 5 rectangles. And we're going to add all 5 of those areas together. So our first one would be the width times our first height, and the second one would be our width times our second height, and our third one would be the width times our third height. The heights keep changing, the width stays the same. Width times our fourth height for the fourth one, and width times the fifth height for the fifth one. Now, since the width is the same in all 5 of these, it might make sense for us to factor out the width and have the individual heights added together. So let's do that. I'm going to factor out the W, the width, and find our individual heights. Now, we said that the heights depended on the function. So h sub 1, we'll call that the first rectangle right here. Right, here's our first rectangle, here's our second rectangle, our third, our fourth, and our fifth. That's fine. So our first one depends on how tall this point is right here. So we need the x-coordinate, and then we need to do f of that x-coordinate. Well, the x-coordinate is just representing the width, so that's 2/5. So f of 2/5 should be that first height. The second height is this point right here. And that's, of course, the second width. So it's not 2/5, it's 2/2, which is 4/5. So f of 4/5 would be our second height. Our third height is right here, and that's 2/5, 4/5, 6/5. So 6/5, f of 6/5 would be our third height. And following this pattern, of course, f of 8/5 would be our fourth height, and f of 10/5 would be our fifth height. I understand that 10/5 is 2, but I'm going to leave it in terms of fifths. So now let's get all of our numbers together. We already know that W, the width, is 2/5, so I'm going to plug in my 2/5. Now I need each of these heights. F of 2/5. Well, that means I'm going to take 2/5 and I'm going to plug it right in here for x. And 2/5 squared would become 4/25. So since I have a fraction, it might make sense to change this 6/1 into, let's say, 150 over 25. Since I'm going to be dealing with 25ths, that might make sense. So 150 25ths take away 4 25ths would be 146 25ths. Let's see what happens with f of 4/5. So I'm taking 4/5 and I'm plugging it right in here for x. 4/5 squared is 16 25ths. And 150 25ths take away 16 25ths is 134 25ths. Alrighty. I'm going to plug in my 6/5 now. 6/5 squared is 36 25ths. And 150 take away 36 is 114. And the 25ths is still 25ths. Let's plug in the 8/5 and I'll have 64 25ths. 150 25ths take away 64 25ths is 86 25ths. And finally, I'll plug in my 10/5. That'll give me 100 25ths, and 150 25ths take away 100 25ths gives me 50 25ths. I'm not going to reduce it because I like that same denominator. If you add up all of these 25ths, and then multiply by 2/5 and reduce your fraction, you will get 212 25ths. And that is our ultimate area of these 5 rectangles. Awesome. So that's only if we have 5 rectangles. The area will get more accurate as we increase the number of rectangles. So this, of course, is left as a fraction because I like that, but if we changed it into a decimal, our area with 5 rectangles is 8.45. If we increase this to 25 rectangles, now I'm not going to show you all that work, but believe me, I did it, the area would be, as a decimal, 9.17. And if we increase it to 100 rectangles, we take this same 2 tick marks and divide it into 100 tiny rectangles and add up all of those areas, we would get approximately 9.29, which is closer. If we take and add 1,000 rectangles together, our area would be approximately 9.33. And if we went outrageously large to 5,000 rectangles, our area would be about 9.3333. So I wonder if you can see, as we're increasing our rectangles, what our area is trying to become, and hopefully you're saying 9 1/3. That's exactly correct. If we had infinite rectangles, our area would be 9 1/3 under that curve. I will show you in our next tutorial how to find the exact area given infinite rectangles, but for this tutorial we are finished with the finite number of rectangles. We just used 5, and we followed this process to find our ultimate approximation of an area. Thanks for watching this tutorial, and I'll see you in the next one. See ya.